Hi, this is going to be a recording for the rest of the examples from our Taylor polynomial approximations notes. This third example is a tabular or table example, and these are very common on the AP exam, so we want to kind of talk our way through how we would generate the polynomial and what else they might ask us to do with it. So the example 3 talks about f and g being differentiable for all orders n. Find the third degree Taylor polynomial for g of x centered at 1, where g of x equals the integral from 1 to x of f of t dt. So we know that we're going to be winding up using fundamental theorem of calculus at some point for this. So if they want the third degree Taylor polynomial, we have to think about what that really would involve. And we have to know where we're centered. So in this case, we would need to know g of 1 plus g prime of 1 times x minus 1 plus g prime of 1 times x minus 1 squared for 2 factorial plus g triple prime of 1 times x minus 1 over x minus 1 to the third over 3 factorial. Where are we going to get these values from? Well, it's important for us to understand that g of x is related to the integral of f of x, and that's going to lead us towards this table. So let's start thinking about things. G of 1 would equal the integral from 1 to 1 of f t dt. Well, anytime the integral is from one number to itself, we know the definite integral is 0 for that. G prime of 1 is going to equal the derivative of the integral. Well, that's where the fundamental theorem comes in. So the derivative of the integral in this case is just going to leave us with f of x. So in this case, f of x at 1 goes to the table, and we see that value is 2. So g prime of 1 is equal to 2. Similarly, g prime or g double prime is going to be the derivative of f of x, and at 1, g double prime of 1 would equal f prime of 1. Again, from our table, that would be -3. And then g triple prime would equal f double prime. And at 1, that would mean that g triple prime of 1 f double prime of 1, and that's equal to 1. So that last value that they gave us is really just there as a distractor. So now we're going to plug in what we know. So our third degree Taylor polynomial would be 0 plus f prime, g prime of 1, which is 2 times x minus 1, and then plus g double prime, which is equal to -3 times x minus 1 squared over 2 factorial, and then g triple prime at 1, which is 1 times x minus 1 cubed over 3 factorial. That's our third degree Taylor polynomial for that first example. Moving on to example 4, there's no table, but there is sort of a list of items that they give you, including a general derivative. So first of all, they say a function is not explicitly known, but that the value at 2 is -7. This value of the derivative at 2 is 0. And then for all the values greater than 1, so second derivative, third derivative, so on and so forth, you have this generic form for the derivative. So they would like to know the fourth degree Taylor polynomial centered at 2, and then they want us to approximate the value of the function at 3. So it's not at the center, but it'll be close to the center. So again, start off by thinking about what our polynomial should look like. So our polynomial at x would, in this case, look like f of 2 plus the derivative of 2 times x minus 2 and so on and so forth. Okay, I'm going to pause it and see if you guys can figure out what the actual terms would look like for each of these 5. Pieces to the polynomial. All right, hopefully you've taken the time and figured out what each of the terms in the polynomial would look like. You can see my answers here. We have -7 plus 0, which is the derivative, times x minus 2, plus, and then I had to use this generic form for the derivative at 2 for each of the next values. I used n minus 1 times 3 to the n, so 2 minus 1 over 3 squared, and then 3 minus 1 times 3 to the third, and then finally 4 minus 1 times 3 to the fourth. And then the rest is the normal Taylor polynomial look to it. That being said, now they want us to use that polynomial to get an approximation for the function at 3. Well, that would be -7 plus 1/9 times 3 minus 2, which is 1 squared over 2 factorial, plus 2 over 27 is 1 to the third over 3 factorial, plus 3 times 1 to the fourth, 81 times 4 factorial. I absolutely would not simplify this. Whatever this turns out to be is going to be fine, but I would not simplify it any more than it already is. So that's example number 4, and then we'll move on to example number 5 in just a second. All right, so example number 5 is sort of a hybrid of examples 3 and 4 because you're going to see a table and you're also going to see that integral look to it again. So they talk about h being a function defined as 4 plus the integral from 2 to 2x of f of t, where f is a twice differentiable function. They always need to include that language so that you know that the derivatives do exist. They would like us to find the second degree Taylor polynomial centered at h equals 1. So in this case, they're looking for p of 2. And I want to do h of 1 plus h prime of 1 x minus 1 plus h double prime of 1 times x minus 1 squared, all that over 2 factorial. Again, I'm going to stop the video in just a second so that you can do this work, but I need to warn you about finding the derivative of that integral. When you do the fundamental theorem, pay close attention to that upper limit. Because that upper limit is 2, it's going to adjust the limits of integration, but it's also, when you take its derivative, going to require chain rule. So think about that as you're taking the derivative, and I'll give you a minute to think about that. All right, hopefully you take the time to try these values on your own. The work that I have is over here to the right-hand side, and you can kind of see for h of 1, I need to do 4 plus the definite integral from 2 to 2 times 1, which is 2 to 2. Like it was in the previous example, that integral part is going to equal 0, so the overall value of h of 1 is 4. h prime of 1 is going to be the derivative of 4, which is 0, plus the derivative of the definite integral, which is going to wind up using fundamental theorem. So I use chain rule. The derivative of 2x is 2. Then I replace the t with the 2x. So I got 2 times f of 2x, or f of, in this case, 2, because h is equal to, or x is equal to 1. And then I have to look at this column over here. And f of 2 is equal to 0. So 2 times 0 is 0. And then for h double prime, I take the derivative of this expression. So it's chain rule again. I would get the derivative of what's inside, which is 2. So 2 times 2 is 4, times the derivative of the outside function, f prime, evaluated at 2x. So that's 4 times f prime of 2x, or in this case, 4 times f prime of 2. F prime of 2 was equal to negative 1. So I got 4 times negative 1, which is negative 4. All that led to my second degree Taylor polynomial, in this case, looking like that. And again, no simplification is necessary. I hope you were able to see how I was able to determine all those values. And if you do the practice problems, you'll see things similar to this in the practice problems.